Hello all. On my back, this is the column to foundation specimen. It is the connection specimen. We are going to test this connection that is made of the column tube. You can see the column tubes at four corners. The column tubes is installed in the column such that when we install the column onto the foundation, it will be the quick installation. We can just screw the nut in and then this column will be in place. So the installation time will be just very short, in around 5 to 10 minutes per column. So this column tube is actually used not only just for the installation purpose, but also it will transfer the force from the reinforcement in the column to the reinforcement inside the foundation. The reason why we have this force transfer because we need to have the moment transfer from the column to the foundation, right? So this column is actually designed to carry the moment, which is roughly about 40 meters around this area. So it needs to transfer that much moment down to the foundation. And the column tube itself, only these four column tubes is not enough just to transfer that much moment. So we have the technologies that we developed in-house, which is so-called the confined-splice. We install the confined-splice inside the foundation such that the reinforcement in the column can transfer the load down to the foundation effectively, and that we expect to have the moment resistance produced by this column to foundation connection to be somewhere around 40 meters. So that is corresponding to the hydraulic jack force, which is somewhere around 20 tons. And we have the load cells over there. Actually, the number, the more precise number is around 18 tons. That is the ultimate level force, and will be read by the load cell. So this is the push-pull load cell that measure both the tension and compression. The information received from the load cell, which is to be plotted in the y-axis, will be put together with the information received from the Y potentiometer that reads the displacement at the top of the column. So this Y potentiometer has the full range of somewhere around 500 millimeters. So this is enough for the test like this at the column head, that we may not expect the drift to be so large. So we need only just less than 25 centimeters on each side. The test will be carried out under the reverse cyclic protocol. So we're gonna produce the displacement at the top of the column at the small amplitude first, and then we're gonna see the hysteresis, and then we increase the drift. So we are going to start from 0.25%. The height of the column is 2 meters. So 0.25% multiplied by the height 2 meters, that ends up with 5 millimeters amplitude back and front. And then we exercise this for 3 cycles. And we increase the drift from 0.25%. The increment will be 0.25% at a time. So from 0.25 will be increased to 0.5. 0.5 corresponds to the drift 10 millimeters. And then 0.75, 15 millimeters amplitude. So back 15, forward 15. And then 1% drift, that is 20 millimeters. So we're gonna increase like this until we approach to the failure of the column. And we just expect that if, originally this column is not designed for the seismic zone, okay, high seismic zone. So actually the ductility is not incorporated in the initial design, because this is going to stay in the low seismic intensity zone. Anyhow, we are testing this under the reverse cyclic protocol, such that we can see if this is the ductile connection or not. So if the drift can reach to somewhere around 3.5%, if it is that ductile, we can claim that this particular column to foundation connection is ductile enough and could be used in the high seismic zone. So let's see if it can go to that far. We have not only just the instrumentation at the top, but we also have the displacement transducer instrumented at the base of the column. So that's going to measure the elongation or shortening over this zone. So from the face of the foundation, top surface of the foundation, to this level of the column. This is the area of which the displacement is going to concentrate, because this is the column two, and the splicing, the confined splice locates just inside this part. So if the deformation is going to occur, that's going to be a lot in here, and moreover, this is the maximum moment area. So we're gonna expect to see the rocking angle, and the damage mostly is gonna start from here. So that's why we instrument from this point. So let's see how far this specimen is gonna go, if it's gonna go all the way to 3.5% drift or not. We're gonna see each cycle we're gonna each drift we're gonna have 3 cycles, and then we're gonna increase. So the hysteresis loop is gonna be bigger and bigger and bigger, and we're gonna see how the ductility would be out of this backbone curve. So let's see in the next step of the test. Right now our specimen has been tested all the way to the drift level of 1%, which is around 20 millimeters or 2 centimeters at the top of the column, of which the length from the base to the mounting point is 2 meters. And you can see that we have a lot of flexural cracks spreading from the base of the column to almost the top of the column. Most of these cracks are flexural cracks. We don't observe the shear cracking yet, and the maximum load that we can produce out of the drift 20 millimeters is somewhere around 17 tons. So we are quite close to the design factor load we want. Well, the hysteresis is still quite narrow, so we do not have a major kind of energy dissipation in the mode that cause the reduction of the capacity, or the pinching is not observed. Serious pinching is not observed yet, right? So we're gonna see how far we will get in terms of the resistance from the structure in the next drift. Right now we are at the drift level of 1%, which is corresponding to the top displacement of 20 millimeters. Now at 1% drift we have the resistance from the structure, which is 17 tons. We are aiming for the target of around 18.5 tons. That is corresponding to the factor moment of 37 ton-meter. So right now at 1% drift, we have 17 ton or 34 ton-meters at the base of the column to foundation connection. Now we are drawing the crack, and you can see that most of the cracks are flexural cracks, as they align perpendicular to the axis of the column. We don't observe the shear cracking as of now, and you can look at the hysteresis on my back. The hysteresis is still very narrow, very thin, so we do not have pinching, serious pinching yet at this moment. So this structure is going to go much further from this point, and we're going to see how ductile it is. It is going to exhibit, and how much strength we can get out of these hybrid, I call it hybrid foundation to column connections, that we have the column shoe and also the confined splice
combined in this particular connection. So let's see in the next clip. Now we test the specimen to the drift 1.5%, and it is still okay. Okay means the load resistance is still increasing. We have the resistance to 20 ton force already by now, which is equivalent to the moment 40 ton meter. This number exceeds the design requirement, the ultimate moment from the design already. So this column to foundation connection passed the requirement now. Actually it passed the required load of 18 tons from the last drift, which is 1.25%, but I forgot to record the video. So we will proceed further. That as we can see now, the hysteresis loop gets fatter, and you can see that the slope is changing already. So we see the initial slope, and then it is less steep at around like 10 millimeters. Well, no, not 10 millimeters, but that's a 12.50 millimeters. So we can see the clear formation of the second slope at this moment. But yeah, the load right now maximum is 20 ton, and it is still increasing. Now, this is after lunch time already. We are at the drift ratio of 2%, which is 40 millimeters at the top of the column. This drift is corresponding to the horizontal load of 20 ton force, and that is the moment at the base of the column, which is about, not about, it is 40 ton meter. So we exceed the requirements of the designs already. The observation we have right now is that from the drift of 1.5%, 1.75% up to 2%, we have this same load. I mean, the load is not increasing with the increasing drift level. That means the connection must be yielding already, but I cannot identify yet which component exactly is yielding. It could be the confined, the steel that is connected to the confined splice, which is yielding, or it could be the column shoe itself that is yielding, or the J-bolt might be yielding. I don't know about that because I don't put the instrumentation in these three components. That could be done, but not yet not in this specimen yet, right? So as the graph is flat right now, the behavior looks like the elastic, perfectly plastic behavior. We have the slope, and then it goes flat like this, like the building in a steel. So the capacity will not be greater than this. We will not see more damage or the crack in the upper part of the column because the bottom or the connection is going to cap the magnitude of the force and the moment, such that we will not expect any greater moment in the upper part of the column. From this point on, everything is going to focus within the connection, and from this point I think we already obtained the maximum capacity of this setup, but we are proceeding to the higher drift ratio in order to learn or to see how far or how much the ductility could be for this particular specimen. So if it is ductile enough, then it can be deployed. This very detail can be deployed for the seismic zone. Right.
So here Since the video was narrated in Thai, I have to do the narration in the studio. So what you are seeing now is a situation when the anchorage to the strong fall was failed at the drift level around 2.5%. It's actually not the failure in the specimen, but it is a failure at the fixture to the strong floor. So we have to do the pull over because the failure is on one side only. Then the specimen will be able to withstand the load, which is going on the pulling side. And as you can see right now, the drift level, as you can see in the screen, is 65 millimeter, which is about it is almost 3.5%. It's actually ductile enough, but as it is not tested, now 3.5% already, as it is not tested under the reverse cyclic protocol due to the failure of the floor anchorage, then I cannot make the nice claim or the legitimate claim, because the tested was not the reverse cyclic, but it is the pull over. Now it is 4% already, but specimen still there. It's not falling down yet, and it is still going. The capacity is reached somewhere around 23 tons, and decreasing right now. As you can see, the figure is falling down because the test was just paused temporarily to remove the displacement transducer to make sure that none of these is gonna be damaged by the failure of the specimen. There are many of them installed there, so I do not want the failure I don't want it to damage the sensors. So we stop the test, and the load drop. So it's not the load dropping due to the uh, the failure of the structure yet, but it is just the load dropping due to the parts of the hydraulic activity, such that the load might be decreasing down a little bit, but it still can go. So the next part, just the load will resume, and you see the load increased to 23 tons already, and the drift level increases to it is almost 4.5% at 90 millimeters. Let's see, you can see the concrete crash out at the column face already, just right before, right? And load is almost 24 tons, 94 millimeters, 95 millimeters. So basically it is approaching to 5% drift for this column to foundation connection using the column tube and the confined-splice technology. Well, the next specimen has to be carried out, has to be anchored to the floor more rigidly, and we might test it at the company laboratory after our strong floor is finished. So right now we exceed the 5% drift. It is 5.5% drift already. 5.5% drift already, and then it is still increasing. So at 120 it's gonna be the 6% drift, and there we go, we are at 6% drift, and the load is not dropping significantly yet. The peak was 24 tons. Right now it is dropping down to 23.5, but there's no major drop of the load magnitude. Now it is decreasing. As you can see, drift is 6.5% and the load is 23. The compression blocks, the face of the compression just scratch out. It is very clear that the concrete just just spouts out and it is dropping down now, and the test is terminated now.